Hello, good evening. Everybody's doing okay? Tonight, in the makeup from Wednesday, we're going to work through the rest of this. Just as a reminder, the exam is next week. I'm currently getting all the materials together, so watch Blackboard either tonight or tomorrow morning. Old exams and answers to handouts and things like that will all go up there, so you can check stuff. As usual, if you're here, you're welcome to ask questions in the chat or on Discord, and hopefully I will see them and be able to answer them. All right, let's take a look at some concentration measures. So last time we talked about two different ways to measure concentration, molarity and mass percent. Another way that we're going to use these ideas is as conversion factors. So remember we said that these different concentration measures really are like something per a mass per volume or an amount per volume. And so when we say 6.0 molar HCl, when we're talking about that as a concentration, another way we can think about that is that that means 6 moles of HCl for every 1 liter of solution. So this gives us a way to convert between moles and liters when we need to. We can also do it with mass percent. So if we have a 63% HCl, percent means per 100. So that means that we're going to have 63 grams of HCl per 100 grams of solution. So let's look at a couple examples. I'm going to do this one first because it's actually a little bit easier than the previous one. What volume of 4 molar calcium chloride solution will you need to provide 0.17 moles of calcium chloride? So the question is asking for what volume. That means that our answer is going to be in probably liters. So liters. And then where are we getting to that liters from? Well, we're given 0.17 moles. So from moles to liters. And to convert from moles to liters, what that's saying is that we're going to use the concentration, it's also given here, 4 molar, and I'm going to show you how we do that. So we start with that 0.17 moles of calcium chloride. And then we're going to multiply it by some factor where we can cancel moles of calcium chloride and instead have liters of the solution. And that conversion right here is the molarity. So we have a 4.0 molar solution, and that tells us that there are 4.0 moles in every liter of solution. So if we do that conversion, we get 0.043 liters or 43 milliliters. It said 2 decimal places, so call it 0.4, but fine. If you actually calculate it out, it comes out to 0.0425, and that's liters. So moles have canceled, and instead we have liters of liters of solution. Okay, let's go back up to the previous question, which is a similar question, but with one extra step. How many grams of KCl are needed to prepare 125 milliliters of this many molar solution? So we've got a couple things to do here. We're given a volume in milliliters, and we're asked for grams. So we want to go from milliliters to grams. Now, depending on what we're doing, we could use different factors for that, like density or something. In this case, we're reading that we're talking about preparing a solution of a certain concentration. So what might that look like? Well, we could take our 125 milliliters and we can't directly multiply that by some molar factor for this thing because we don't have liters, we have milliliters. So we have to convert to liters because we know that molarity is moles per liter, not per milliliter. So that means we have to cancel milliliters and instead have liters, and we know that conversion. It's 1,000 milliliters per liter. So now we have liters. Now we can use the molarity and cancel liters and instead have moles of KCl. So the molarity is 0.720. So that's 0.720 moles per 1 liter. So now we've canceled liters and we've got moles. But again, we're not asked for moles, we're asked for grams. So we have one more step where we have to convert from moles of KCl to grams of KCl. And to do that, we're going to have to use the molar mass. So we would add up the masses of K and Cl on the periodic table. I'm going to look that up real quick here because I can't see it if I bring it up on the screen very well. And it's about 75, say 74.6 grams per mole. So to evaluate this, we take our 125 and divide by 1,000, multiply by 0.72, and then by 74.6. And we get 6.714 grams of KCl. So what that means is if we took 6.714 grams of KCl, we put it in a flask, and then diluted it to 125 milliliters, so the total volume is 125 milliliters, we would have a 0.72 molar solution. So we're preparing a solution of a given concentration, but we're figuring out how to do that by just treating everything as a conversion and going from milliliters to liters, then moles, and then grams. All right, and then we can do a similar technique with the mass percent. So in this case, instead of asking how many grams of something are needed for a certain molar solution, it says how many grams of this are needed for a mass percent solution. So in this case, we've got 225 grams of solution. And we want to know how many grams of sodium chloride to put in. Well, if we want a 10% solution, that means we need 10 grams per 100 grams of solution, because that would be a 10% solution, 10 per 100. So we do that, and we've got 22.5 grams. This one you could almost do in your head, because if it's a 10% solution and we know we want to make 225 grams total solution, then 10% of that is going to be the sodium chloride. So we didn't really necessarily need to do the whole conversion thing for this one, but sometimes it's helpful to just have that same way of doing it every time to make sure that you're correct. All right, let's talk about dilutions. So how do you make lemonade? Well, I guess it depends on what type of lemonade you like. You could make it from lemons and sugar. That'd be like the fancy fresh lemonade. But I think what this is actually referring to here is the less fancy version, but still delicious, like Country Time lemonade or Minute Maid in the frozen can or whatever, where you have some sort of a powder or a concentrate, and then you add water to it to get it to not be so strong and to taste good. So this is really the key thing here. Does the amount of solute change when you dilute something? It does not. So when you have a solution of whatever concentration, when you dilute it, when you lower the concentration of that solution, what you're doing is you're adding water. So you're adding water or solvent in general, but you're not changing the amount of solute. You're not changing the grams of solute. You're not changing the moles of solute. You're only changing the volume of water or other solvent that's being added. And so because of that, because that amount stays the same, there's a little bit of a shorthand equation for doing dilutions. So it looks like this. Ci times Vi equals Cf times Vf. So Ci is the initial concentration, Vi is the initial volume, so the thing that you're starting with, the solution you're starting with, and then the final is after you've diluted it, after you've added more water. The reason that works, if we think about molarity, molarity is moles per liter. And so if we multiply a molarity times a volume, we get moles. So all this equation is really saying is that the moles of solute have to stay the same. And so you can kind of do this in whatever units you want, as long as the volume unit cancels whatever the denominator of the concentration unit is. So for example, number 28 here, what is the molarity of a solution prepared by diluting 0.180 liters of 0.6 molar HNO3 nitric acid to 0.540 liters? Okay, that's a lot of numbers. Let's think about what's going on there. We've got a 0.6 molar solution, and we're going to and then our initial that's our initial concentration, and then our initial volume is this 0.180 liters. So we've got 0.180 liters of a 0.6 molar nitric acid solution, and we're diluting it to 0.54 liters. So it's going from 0.180 to 0.54. So we're increasing the volume by adding water. So let's identify the terms of this equation, and then we can solve for it. So the initial concentration is 0.6 molar. The initial volume is 0.180 liters. The final concentration is what we're trying to figure out. We don't know that because it says what is the molarity, right? That's the final concentration. And the final volume is 0.540 liters. So now we can simply put in the equation and solve for the final concentration. So that's 0.6 molar times the initial volume, 0.180 liters. And that's going to equal the final concentration times the final volume, 0.540 liters. All right, so to solve that, we just multiply these two and divide by 0.540. So 0.6 times 0.18 divided by 0.54 is 0.2. We'll keep our three significant figures here. So our final concentration is 0.2 molar, or 0.200 molar. All right, so the next one, I'll leave that one for you to try. Notice that this one is in milliliters instead of liters. But here's the thing, you don't actually have to do any conversions because it's milliliters on both sides. So if you've got milliliters on the left and milliliters on the right, and then you divide by the one on the right, the milliliters are going to cancel and you're going to end up with molarity. So when you do this dilution equation, as long as the volume units are the same and the concentration units are the same on both sides of the equation, you don't have to convert anything, unlike the concentration calculations we did before. So you can do that in just the same way. All right, and then here's some more practice. These are all kind of general practice of all those concentration types. So let's just pick out a couple and solve them. What is the molarity of 325 milliliters of a solution containing 46.8 grams of NaHCO3, sodium bicarbonate? Well, we have to remember that molarity is moles per liter. So we need moles of solute, sodium bicarbonate, and liters of solution. Liters of solution is easier because we've got milliliters, so we can just move that decimal place. And we know that that's going to be 0.325 liters of solution. So we know that's going to go on the bottom. And then the moles is going to give us a little extra step here because we have to calculate how many moles of sodium bicarbonate. But we can do that. 46.8 grams of sodium bicarbonate times to convert from grams to moles, we need the molar mass. So we can calculate that from the masses on the periodic table. And we get about 84.0. So that's going to be 46.8 divided by 84, 0.557. That is moles of sodium bicarbonate. So now we've got moles, we've got liters, so we can calculate molarity. 0.557 moles of solute divided by 0.325 liters of solution is 1.71 molar. So this solution's concentration is 1.71 molar. All right. So give these a try. Make sure you can do these types of problems because you will see these on the exam next week. And let me know if you're running into problems. I will post the answers to these so you can check, but make sure that you're comfortable working through them on your own. Okay. So that's the calculations from this unit. And so the next part is just a few definitions of some different ways of talking about mixtures. So there are some different kinds of mixtures. We've talked about the difference between homogeneous and heterogeneous mixtures, but there are some other ways of describing them as well. So we just talked a lot about solutions being a type of mixture, a homogeneous mixture. There are a couple other important types of mixtures that involve something that are similar to solutions, but different enough that we need to carefully define them. And that is colloids and suspensions. So solutions are a homogeneous mixture, whereas suspensions are a heterogeneous mixture. And we're going to leave the colloids for last because you'll see they're kind of a weird middle ground. So the solutions are homogeneous, suspensions are heterogeneous. Suspensions, as we fill out this table, you'll see them defined. So particle size, solutions particle sizes are very small. They do not reflect any light at all. A solution looks totally clear. It can be colored, but it looks clear. So, you know, the particles are like on the side, on the order of a molecule type size. Whereas a suspension, the particles can be large. So if you imagine something that you have to shake up to distribute, and then if you let it sit, the particles settle down, that's what we're talking about when we talk about a suspension. We're going to skip this middle one for a second. We'll talk about that later. Filter paper. So we filtered stuff in lab, just like half of you did on Wednesday, and the other half of you will do after the exam. If you put something through filter paper, like a coffee filter, a solution will pass directly through that. So if you take something like a salt water or sugar water, you pass it through a filter paper, that filter is not going to separate those sodium chloride particles or sugar particles that are in solution because they're just too small. So the whole thing goes through the filter paper. But a suspension, the particles will not pass through the filter paper. The solids will be on top and the liquids will go through. Because again, those suspension particles are much larger. Will they settle out in a solution? No, you can leave a solution as long as you want. Everything stays together. But a suspension, you have to shake it up, and then if you let it sit, those particles will settle all the way down to the bottom of the bottle. And then, let's go back and talk about colloids. So there's this weird middle ground where the particles are not big enough to really be suspensions, because they actually make a homogeneous mixture. And they have small particles, but they're smaller than suspension, but larger than solution. So we're thinking about things like proteins, starches, so things with really high molecular weights compared to small molecules, but not so big that they're like a clump that would fall out of solution. So these are like your cloudy sort of solutions where everything's stuck there, nothing's settling out. Colloidal particles will pass through a filter paper and they will not settle out. So in many ways, they behave like solutions, but they are cloudy, and those particles will not pass through a semi-permeable membrane. We're going to talk about that for the next little bit. A semi-permeable membrane is a kind of like a filter, but the holes or the ways that particles can get through are extremely, extremely small. And they're meant to be similar to like a cell membrane in a living thing. So something that certain things can diffuse through, but larger things really can't. And so those particles will pass through a semi-permeable membrane. Colloidal particles will not. They're too big, and suspension particles will not too. So that is really these two columns are really what differentiate a colloid from the other two, is that they're too big to get through the semi-permeable membrane where the solutions can do that, but they're too small to be trapped by a filter paper. So they're kind of in between. All right, so some examples, we could say salt water here for a solution. A colloidal mixture might be something like one that I always think about is homogenized milk, which is the milk you get at the grocery store, where you can't see through it. Light can't pass through it. There's definitely particles in there, but they don't settle down to the bottom of the milk jug either, because those particles have been broken up so small, fats, proteins, things like that, that they can stay suspended in that colloidal state. And a suspension would be, anything else that you kind of have to shake up. So like those kids' medicines, like the pink amoxicillin that you have to shake up before you give it. Salad dressing, let's say vinaigrette. All right, a salad dressing that you have to I'm not even sure I spelled that correctly, but a salad dressing that you have to shake up, and then if you let it sit, the particles settle out. So using these ideas, you can differentiate between pure substances, solutions, suspensions, and colloids. All right, so thinking about these semi-permeable membranes, let's look at this idea of tonicity and how the amount of solute can affect a blood cell that and this is not just applicable to blood cells, but many other types of cellular environments. We talked about how a cell membrane is a semi-permeable membrane. So particles that are in solution can pass through that membrane. And in fact, they do. And two processes are going on here, where I'm going to just jump down here. I feel like it makes more sense to define it first and then go back up. Two things are going on here: diffusion and osmosis and dialysis. And you may have heard these terms before. Let's define them. Osmosis is the flow of water through a semi-permeable membrane. So just water. Whereas dialysis is other solute particles also going through that membrane, that semi-permeable membrane. And so the thing to remember here is that all of that stuff is always going to move from areas of higher concentration to lower concentration of whatever it is you're talking about. So water moves through the membrane from a place where there's more water to a place where there's less water. And also solutes move through the membrane from a place where there are fewer solutes to a place where there are more solutes. And those are opposite. So because of that, I'm just going to draw a picture here. You can kind of set something up like this. Let's say we have a container and we put a semi-permeable membrane in the middle. And I think there's some pictures of this that are a little better in the linked book chapters. All right, so we've got a semi-permeable membrane separating two sides of a container. And then we've got some water. All right, so there's water on both sides. And water molecules are going to be able to pass back and forth essentially evenly if this is pure water through this membrane. So now let's say it's not pure water anymore. Let's introduce some solutes. So we'll put some sodium and chloride in this, but not in the other side. All right, so now there is higher solute concentration on the left, lower solute concentration on the right. So what's going to happen here is the water molecules are going to move from where there is more water to where there is less water. So all the water molecules here, water molecules are going to primarily move from right to left across this membrane because they're trying to equalize that concentration. They're trying to go from, or they're trying to stop that pull. Well, that's not really the right way to say it. The interactions between water and sodium and chloride on the left side are causing more water molecules to flow over from the right side. And this actually creates a pressure because, of course, there's an atmosphere up here. So when the water moves across this membrane and the water level starts going up, that's pushing against the atmosphere. So this chemical force or phenomenon is actually exerting a pressure, and that pressure is called osmotic pressure. So the pressure being exerted on that membrane by water is known as osmotic pressure. Now, in the same time, these ions are going the other direction to, again, try to equalize the concentration. And over time, water will have moved to one side, the ions will move to the other side, and over a long enough period of time, everything will equalize in concentration. And so when that happens in your body, that can be good thing, that can be a good thing, but it can also be a problem. So when we look at a blood cell, we need the solution around the blood cell, so the blood, to be the same ionic and solute concentration as inside the cell, because otherwise water is going to move either into the cell, which is not good because it could swell and burst, or water could move out of the cell, which is also not good because it could shrivel up and die. So ideally, we have what we call an isotonic situation, where there are the same numbers of solute particles on the outside of the blood cell as there are on the inside. And that way, everything kind of equalizes and that cell isn't forced to contain more water or lose water. But when those change, we can get some less favorable conditions. So if a solution is hypertonic, meaning that there's lots more solute outside than inside, hyper means high, so we're saying that the fluid out here is much higher concentration of solute than the fluid inside the cell. So think about what happens to the water then. Water is always flowing from where there's more water to less. In this case, there's more water inside the cell because the outside has a higher concentration. So water is moving out of the cell, and eventually that's going to collapse the cell, and that's called crenation. The cell kind of like shrivels up. If the opposite is true, if we have a hypotonic solution, so let's just say we have a very low solute concentration outside the cell and then a higher concentration inside the cell, then we have the opposite movement of water. So water is going to move into the cell, and that's going to cause the cell to burst and also die if enough of it gets in there. And that's called hemolysis or just lysis. So what you should know, there are a couple concentrations that you should know. Sodium chloride, the normal concentration of sodium chloride, or the isotonic concentration, is 0.9% mass by volume. And the normal concentration of glucose in blood is 5% mass by volume. So if, like you are hooking up an IV bag or something like that, you would expect that you'd have similar concentrations so that you don't have these things happening to blood cells. There are some cases where a doctor might want to very carefully, purposefully have some hypotonic or hypertonic solution going in to like in emergency situations, but it is dangerous. So generally, if you just want to give fluids, those fluids have to be the same, have to have the same type of particle concentration as the as inside the blood cell. And because it's based on the count of the particles, that will be the same molarity will always be isotonic, but the mass-based concentrations will change. And we're going to get into this more in a couple weeks with the next lab, the solution suspensions and colloids lab. Yeah, I think that's it here. So this last stuff about the solutions and suspensions and colloids will not be on the exam next week. We'll leave that off and wait until we complete the lab. So this stuff will just show up on the final. All right, so let me know how you're doing with that. Make sure to practice the calculations. This is really the first exam with a significant number of calculations on there. So you've got your unit conversions and moles and stuff from that chapter, and then solution concentrations as well. So that's probably where you want to spend the bulk of your time, but also don't forget the other kind of conceptual stuff in between, the Lewis structures, the what else? Ionic compounds. Make sure you can still name your compounds, refresh your memory on that if you need to. And then gas laws, polarity, intermolecular forces, all that stuff too. So next week, the live sessions on Monday evening and Wednesday morning will be purely exam review and questions. So bring your questions. I'm not going to have anything in particular planned, so whatever it is that you want to go over, come on those days and ask your questions. And yeah, happy studying and hope everything's going okay. And I will see all of you on Wednesday for the second exam. All right, good night, everybody.